Thanks a lot for the introduction, and thanks a lot for the organizer. So today I'm talking about multi-party computation in the plane model when we want to make black box use of the primitive. This is based on a set of joint work with my beautiful collaborators that are Michele, Rafi, and Hendrik. So let's start with the setting. Amazing, yes. Yes, sorry, I'm a bit nervous. Anyway, so let's start with the setting here. We are in the plane model, which means no setup, no random oracle. We want to be secure in a dishonest majority setting, which means n-1 party can be corrupted. And we know that in this setting, due to the cleaving possibilities, one of the best notions that we could achieve is unanimous abort, which means that in this setting, the adversary can recover the output, even when the honest party don't. So the adversary can decide if the honest party are getting the output or not. Okay? And in particular, here we are interested in the notion of security where the simulator has only black box use of the adversary, which means that the simulator can only make black box query to the adversary. Okay? So that's the setting where we are in. And in this setting, one of the most studied questions is what is the round complexity of those protocols? How many rounds are necessary and sufficient to realize those protocols? Why this question is important? Well, this is important from a point of view of efficiency, because in a very high latency networks, this determines how many times, for how much times the party needs to be online. Okay? So we know from previous results that the optimal round complexity is 4. So 4 rounds are necessary for realizing those type of protocols. And we also know since few years now that that we could actually achieve those protocols for any functionality using just using OT. But those protocols don't make non-black box use of the underlying primitives. What does it even mean? Well, it means that what does it mean to have black box use of the underlying primitive? It means that we look just at the input-output behavior of the primitives. So in this setting, until this work was making non-black box use of the underlying primitive. So the question is the landscape changing when we are making the black box use of the primitive, or we do have still the same matching upper bound? Okay? And so there is a more recent line of work that was studying this problem. So the work of Shai et al. Gave a protocol that was 5 rounds for any functionality, and a subsequent work gave an optimal round protocol, but making sub-exponential assumptions that are secure with sub-exponential adversary. So and then into subsequent work, we finally close this gap, giving a 4-round protocol that first was working for any inputless functionality, and then we solved it for any type of functionality. Okay? So in the rest of the talk, what we are going to see is principally how to solve this question, and what is the approach to solve this question. So we start with the main building block of this type of work, that is the IPS compiler. How the IPS compiler works? Well, it's a set of different protocols that are put together and each of them they have a weaker guarantee, and in such a way that the final protocol have stronger guarantees. Okay? So the first building block that we are interested in is an outer protocol that is in the client-server setting. In particular, here we have end clients and M server. And the communication is that there is a single message to the client to the server, there is a local computation of the server, and then there are messages back to the client. Okay? And here the protocol is secure against n-1 corruption of the client, but only 1/3 of the server can be corrupted at the most. So there is a threshold of only 1/3 of server that can be corrupted, while what we want to achieve is that n-1 party can be corrupted. So how is possible to modify this protocol in order to achieve this guarantee? Well, we are going to rely on another building block that is called the inner protocol. The inner protocol is secure against the dishonest majority, but only in the semi-honest setting. And now the idea is that each inner protocol can emulate the computation of one of the servers. So all the computation is emulated, each server is emulated by a computation of the inner protocol. Okay? So we have m execution of the inner protocol in parallel. Okay, but notice that each single building block are secure only with the semi-honest adversary. Okay, so right now, still the adversary can just go and since he is active secure, can just go and behave malicious in all of them. So how we are going to ensure that this is not a problem? We are relying on a third tool, which is the watchlist functionality. So the watchlist functionality is basically, it establishes a OT correlation between the parties in such a way that some of these instances at random can be checked in a way that the adversary or the other party doesn't know which of the instances are checked. So to not be caught, the adversary needs to behave honest in a lot of them. Which means that he can behave malicious just on a few of them. But if he behaves malicious in a few of them, then the security of the outer protocol can be invoked to establish that the entire protocol is secure. Okay? That's the general idea of the IPS compiler. Now, how we are gonna, and now, to realize our MPC protocol, we are gonna squeeze this building block all together for realizing a 4-round protocol. So in the rest of the protocol, in the rest of the talk, we are going to see how it's possible to squeeze this building block together. Remember that we are in the plain model, so there is no setup or random oracle. So the first observation that we want to make comes actually from the work of Ishai et al. And basically, they require some extra property on the inner protocol. Now the inner protocol is not anymore semi-honest secure, but is semi-malicious secure. And also, it requires the extra guarantee that even if the adversary is behaving malicious in the first 2 rounds of the inner protocol, is still that the input of the party are not linked to the adversary. Okay? Moreover, we are going to ask that it's sufficient to run the consistency check on the first 2 rounds of the inner protocol. So in this setting now, we are not going to check the entire execution of the inner protocol, but it's sufficient to guarantee that the protocol is secure that we are going to check the consistency of the first two rounds of it. Okay? So if this is the case, then we can squeeze some of the round. In particular, it's possible that the watch list completes in the 4th round, and we can squeeze the first 2 rounds of the inner protocol at the same time of the last 2 rounds of the watch list protocol. Because when the watch list protocol is going to end, then we can go and check the consistency of the inner protocol. Okay? And we know from the work of Ishai et al. How to realize this watch list protocol in 4 rounds. Okay? So this will make the final protocol 5 rounds. This approach will make the final protocol 5 rounds. So what is the principal bottleneck to have this in 4 rounds? To squeeze 1 more round and have the entire protocol in 4 rounds? Well, the problem is that this watchlist protocol establishes OT correlation. So we know from the same lower bound of the coin flipping that this protocol needs to have at least 4 rounds. Okay? So there is actually a main bottleneck here, is that this watchlist has to have 4 rounds. Okay? So what is the approach here is to relax what we need from the watchlist, is to ask for at a very, very high level, what we are going to ask is for a weaker form of setup to establish the IPS compiler. Okay? In particular, we are going to ask a weaker notion of security that is called sometimes aborting adversary, which means that, that we are going to able to simulate only if the adversary completes the third round. If the adversary does not complete the third round, we are not going to give any guarantees of security. So this protocol is secure only when the adversary actually completes the third round. Okay? This is one of the weakening. The second weakening is what is the functionality that we are going to realize. Okay? We are not going to realize anymore. So just as a recap, the watchlist functionality was establishing OT correlation between the parties. Now we are requiring something less. Okay? In particular, let's just see it for the case of 1 out of 2 OT. Okay? So we want to establish just one OT correlation. So how this is going to work in the standard setting? Well, in the standard setting, and we are looking at that from the point of view of malicious receiver. Okay? How this is going to work in the standard setting? Well, the adversary select a bit, and then here we are the input of the sender are actually random string, so are sampled by the functionality, and then one of them is sent to the adversary based on his bit, and then since we are in the unanimous abort setting, is the adversary to say if this pair of strings are also getting to the sender. Okay? That's the standard one. That's the standard OT correlation. How we are going to change it? Well, let's see. So in this setting, still looking from the point of view of malicious receiver, what we are going to do is that first of all, the adversary sends 2 parameters now. He sends the bit that he wants to recover and a set of and a parameter k, which determines how many pairs of string the functionality needs to get. So now we don't have anymore 1 pair of string, but we have k pair of strings. Okay? And the adversary is going to get all of them. Okay? And then he's going to decide which one he likes among this set. And he's going to decide if the sender is getting it or not. Okay? So why this change things? Why this is possible to be implemented in 3 rounds, while the normal that we have on the normal OT correlation that we have on the right is going to have 4 rounds? Well, there are 2 main takeaways. I will not go too deep in the details, but there are 2 main takeaways of why this is possible. Well, first of all, here the input of the sender are random, which means that the simulator, when acting with a malicious receiver, it can actually act exactly as an honest sender would behave. Okay? So his input and the input of an honest sender are actually perfect. They are distributed identically. Okay? So this gives the possibility that when we are extracting from the receiver, the view of the receiver is exactly as the one that he has in the real world. Second important point, now this is a way to the adversary to actually bias a little bit the OT correlation. Because now he's going to not have one single result, but he can choose among a set of them. And why this is important? This is important because the simulator now has multiple attempts to actually fix one of the values. So at a very high level, we can demonstrate that if the receiver succeeds in the main thread, then we have multiple attempts to actually finish this protocol again. And we can demonstrate that this terminates in a polynomial number of tries. And the second time that the receiver terminates is the string that I am going to get. Okay? So the simulator at this point, it chooses the ith pair to send to the sender. Okay? That's a very, very high level why this relaxation is possible to achieve in 3 rounds, and this is 4 rounds. At even a more high level, in this case, the adversary can bias a bit the OT correlation, but in such a way that it's not going to hurt the entire protocol. Okay? So then from we have the list. We construct this list 1 out of 2 list simulatable from private to T in 3 rounds, and we have some extra property that I will not go too many in details in. And then from that we construct a K out of N of T, and then from the K out of N of T we construct a list to PC for some certain functionality, and from that we rely on a similar approach of the work of Ishai et al. To construct finally our watch list. And with our, let's say, our special edition of the watch list functionality. Okay? So now we are going to have, we have this special tool. How are we going to use it? Just to recap, this special tool is weak, not only in terms of the functionality, but also in terms of the security that we are going to get, because if the adversary aborts, we cannot claim any security of the entire protocol. Okay? Why this is a problem? Let's see. So this is a problem because when I am running this, remember that our idea is still to have everything in 4 rounds. So we need to run the last 2 rounds of the watch list, that now is 3 rounds, with the first 2 rounds of the inner protocol. Okay? So, but now the adversary is rushing. So what he can do is to get the 3rd round of the inner protocol, but not sending any message. And this could potentially leak the input of the honest party, because the inner protocol contains the input of the honest party. So this, because in this setting, if the adversary does not complete, we don't have any security of the watch list. Okay? So if we don't have any security of the watch list, we can basically not extract the T correlation, and then we cannot claim the security of the entire protocol. So at a very high level, the problem is that, at a very high level, the problem is that this round contains the input of the honest party. So how are we going to solve that? Well, we work a bit more with the inner protocol. We require something even more from the inner protocol. Now this inner protocol is going to be divided again. Okay? And we are dividing it in 2 parts. The first part is going to be inputless. This part is going to be inputless, and this part contains still the input of the parties. And now what I am going to ask at a high level is that if the adversary behaves honest here, then we can claim that the entire protocol is active secure. Okay? So to claim that the adversary is behaving honestly is sufficient to check the consistency of the inner protocol, only for these first 2 rounds. Okay? Without touching at all these messages. So how is going to be now? Well, the watch list still has is 3 rounds, and now we have the 2 rounds of the inner protocol, and then we have one of the round of the inner protocol for the input, which also contain the input of the party. Okay? So it seems that this modification didn't change anything, because still, if the adversary does not send this message, the inputs of the party are leaked. So it does seem that we didn't change much in the final protocol. Okay? We actually changed one thing, because here is possible just to check the consistency of those messages to claim that the entire protocol is secure, which means that at this point in time, actually the party don't need yet those messages. And they are going to need them only if the adversary finishes this round. Otherwise, they just don't care about this message. Okay? And the protocol can be aborted securely, because only this message contains the input of the party. So we need a way to disclose those messages only when the adversary finishes this round. So And what is this? Well, it's a conditional disclosure of secret. Okay? So, in particular, we want to put this orange message in a box. And when we are computing these third round messages, we are just sending a box. This box, so the third round message that contains the input is completely encoded. And it's just sent to the party in an encoded way. And now, at this point, the party can check if they retrieve the other messages from the adversary. And only if they retrieve the third message from the party, they can send the key to unlock this box. So we are protecting the third round of this third round that contains the input of the party using a conditional disclosure of secret, which will be revealed only if the adversary actually completes the third round, and then we can rely on the security of the watch list. Okay? So what is the caveat here is that this process alone will be 4 rounds. But in 4 rounds, we want to finish all our computation. So this box has to do something more. This box has to give us in output also the third round of the inner protocol for the input part. How are we going to do that? Well, we are going to use Garble circuit. Okay? So in particular, the inputs of the party is the second round of the inner protocol. And they compute the next message function of the third round of the inner protocol. Okay? So now the only caveat is how I'm going to get the correct label for evaluate my Garble circuit. Okay? Remember, I can still not send this message in clear, because otherwise the security of the entire protocol is leaked. So how am I going to do that? Well, I am using an OT. So we are using one more oblivious transfer that is fully simulatable at this point. So this OT is fully simulatable, and the idea is that, well, let's see. If the watch list does not terminate, it means that I can invoke the security of the OT to claim that this message is still protected. Okay? So, and basically, I can safely abort. If the watch list is going to terminate, then I can rely on the security of the watch list to claim that the entire protocol goes well. I can exploit the IPS compiler. Okay? So if the watch list terminates, I will rely on the mechanism of the IPS compiler. If it does not terminate, I will rely on the security of the OT. And I am sure that my message is protected because it's the receiver message of the OT. So what are the subtleties here? So first of all, well, we need to make sure, because remember, the entire goal is to make black box use of the primitives. So the garbling of the next message function does not need to contain cryptographic operation. So we are going to make sure that we divide the protocol in such a way that the garbling of this next message function is actually safe. Okay? And moreover, we have a second problem, is that now we are in the multi-party setting. So this means it's not only one OT, but there are multiple OTs that are played at the same time. And well, an adversary can just play different third round of the inner protocol in different OT. And the security of the inner protocol just says that I am going to see one message of one type of message for the adversary. And then the protocol is secure. But if I am able to retrieve multiple fourth round messages, then I cannot invoke the security of the inner protocol. Okay? So we need to work around also around this problem to claim the security of the final protocol. So intuitively, what we want to have is this situation. So we have n sender on the right, And what we want to guarantee is that if the adversary chooses the bit B, then the only thing that is going to reconstruct is the label corresponding to the bit B for all the possible sender. So we want this final output, or that it doesn't reconstruct anything at all. So how we are going to do that? This is from some previous work, and the idea is as follows. So each of these person is a garbler, right? So each of these person is a garbler, and what it's going to do is to additive secret share is label, okay? Both for bit 0 and for bit 1. And then it's going to communicate privately to each of the party one of this label, okay? And this is done symmetrically for all the parties. So which means that in the end, all the party, they are going to have a secret share. They are going to have a piece of the label of all the other guys, okay? And now they are going to play their T using these new pieces, okay? And this is doing symmetrically for all the party, which means that the adversary is getting the correct label only when he plays consistently in all the OT. Otherwise, he will get, in one point, a label for a share for the label of 0, and in another point, the share for the label of 1. Okay? So that concludes the presentation. So what is one of the main takeaway of this work, of this two work, I think, is that the watch list that we are realizing is actually weaker than a normal OT correlation. Okay, it's weaker, but still is enough to claim that to realize 4-round protocol for any functionality using just polynomial time assumption. And maybe those type of setup could actually be used in a. So this is one example of application of where this watch list can be used, and maybe can be used elsewhere. Okay? So some open question. As I was saying, our work is based on private OT, so which means that for semi-honest, with the black box use of semi-honest OT is still open. Our protocol is secure against the unanimous abort, but is not secure in the case of identifiable abort. And finally, the communication complexity is humongous at the moment. So, and that's conclude the talk. Thank you.
Follow-up questions?
You assume OT. What is the one complexity if you don't assume OT?
So it's 2-round private OT. We start from 2 rounds private OT.
If I don't assume OT, what is the one complexity that we can get for protocol?
For MPC protocol?
Yes.
If you don't assume OT at all, you...
Yes. You can construct a protocol for OT, but not...
sorry, I didn't...
I don't want to
It
assume...
means without the black box restrictions.
Without the black box restriction. Without making black box use of OT.
I can construct a protocol for OT or do something else. Right?
Yeah. Then you still get 4 rounds from other assumption.
With black box simulation.
With black box simulation, yes. Yes,
Maybe the question is without the black box simulation.
Without the black box simulation, okay, without black box, thank you. I don't know with respect to black box simulation, but I believe it can be different around complex because the lower bound actually exploit that the simulator is black box. So it can change in that setting. Yeah.
Additional questions? If not, let's thank Luisa again. All right, so we now have 2 hours for lunch. Please come back at 1:45. And this is your last opportunity. We'll be closing the senior, junior